its own affinity.
So it has a nested routing table.
Hi, everyone. My name is Kumar Kartikeya Dwivedi. I'm a third-year PhD student at EPFL, and I also work part-time at Meta. So this was like sort of a exploratory research project that I started with a few folks at Meta, Ravi, Andri, and Tejun. And basically the goal was to figure out whether we can extract more information about workloads and then use that to guide scheduling decisions. So let's get started. So some background on where this is coming from. So internally, we experimented a lot with custom schedulers and fine-tuning several scheduler that we have in the SCX repo that we use internally to basically optimize specific workloads and tune its behavior to them. And what we noticed is that when trying to generalize these heuristics, a lot of them do not generalize well for all of these different workloads. So one example is when you're trying to do cache-aware scheduling. So there's a deficit of information available to the scheduler to make optimal decisions. The second sort of scheduler decision that doesn't work well is deciding whether to trade work conservation or migrate instead to some other CPU in search of ignoring locality. So all of this basically comes from some lack of information about the underlying characteristics of the workload, whether it prefers locality or whether within the threads of a workload, there is a lack of locality or not. At the same time, there are we experimented with hints as well that are passed from the application to the scheduler, but these are also not completely sufficient on their own. One of the reasons for this is that the ground truth with respect to things like locality keeps shifting based on runtime input. For instance, the traffic mix that the workload is seeing, and also the constant code changes that keep happening to the workload. The second problem is that sometimes the service writers themselves do not understand what would be the right scheduling behavior for their workload. So in all of these cases, we end up falling back to very conservative approximations and very simple heuristics on what would make sense. So there's this tension between specialization and trying to scale that process in that it's very valuable to spend time on something like this for getting more efficiency, but you have to repeat that process for every workload, and then you also have to maintain and debug problems that arise from that process. So it's not very convenient to scale. So as I said, there is this gap between the scheduler and the workload. And sometimes when information about the workload is available, we are able to exploit it to make better decisions. So one example is PELT, where we keep a history of the load characteristics of a workload. But otherwise, as I said, let's say we have to decide between exploiting locality or going to some other idle CPU. There we do not have enough information to make an informed decision. So basically the two questions that I will try to answer with some experiments and some open-ended questions is that how do we bridge this gap between the workload and the scheduler? And then how do we design heuristics that are parameterized by the richer information that we can get from the workload? So one example here to illustrate why this gap exists is cache-aware scheduling. So a very simplifying assumption we can make is that different processes naturally do not share their caches because they don't share the address space. So this works very well for us as well because we have a lot of maintenance jobs on the machine, sharing the machine with the main workload, and we just partition them away to avoid cache perturbation. But when we start thinking about more differentiation, right? For instance, how do threads within the workload behave with respect to locality? What is their temporal and spatial pattern of sharing data?
So this first thing is already broken by PostgreSQL because they have a giant array of shared memory that contains the database, and they do inter-process communication.
Yes,
like
yes. So that's why I wrote typically. But like if you have such shared memory regions, yes, you will end up sharing them across processes as well. That's true. Then like one of the other questions to ask is, when we have some request processing service, do we have locality between request types or some lack of locality? Then when we have a request type, do we have locality in some specific phase of the request? And then sort of the white whale question of all of this is like, how quickly does my cache decay as a function of other things that share the cache domains with me, right? So suppose I went to sleep and I wake up and have to decide whether I run on my previous CPU or LLC. How do I make that decision whether I would benefit from the remaining locality there if other tasks have run on that domain already? So the second example of this is, should we be trading work conserving behavior to stay tied to the task's prior cache domain? Or should we instead go for any idle CPU that we can find on the system and ignore all bias for cache affinity? So in this particular case, as I'll demonstrate later, for some applications, the answer is tied to their tolerance of the scheduling latency. So, and this tolerance itself is not a fixed value that you can set for a workload and forget. It depends how loaded the machine is, which class of application this is, whether it cares more about latency or less, and whether that specific thread is doing something latency critical or not. So this whole thing becomes beneficial if sticking to the domain gives us a speed up that is more than the scheduling delay that we will incur by staying there. So throughout this talk, the theme will be that we try to collect some signals offline and online to better characterize such behavior for the workload. And the focus will be around cache locality to keep things focused. And then we try to adapt various scheduling related decisions that we make at both push and pull time to take this data as input. And one of the ways we are going to enforce locality between different groups that we identify as sharing data is creating soft partitions, which are basically dynamically sized CPU sets that the scheduler will scale up and down based on the utilization. And then if we do something like this, we see that co-locating these threads leads to lower misses for the application, which overall leads to lower stalls and higher IPC on the system. And I think like one learning for me, at least, since I started doing all of this just a year ago, is that making the right placement decision over a longer period of time gives a bigger benefit than trying to make that decision quickly, because where it is placed affects the runtime of the application and what the microarchitectural metrics of that application will be. So I will use one of our workloads as a running example. So this workload called web serves like the web page for facebook.com. It's also the inspiration behind the SCED-Bench benchmark, which Chris Mason created. And the reason is that this particular workload is very sensitive to scheduling behavior. So for instance, lack of work conservation is instantly visible in the metrics that we track. And then involuntary context, which is show up as throughput loss. And for all of these experiments, we are going to use a scheduler called layered, which is like for the purposes of this presentation, two details that we need to remember. It's a soft partitioning scheduler, and it uses shared DSQs to be work conserving. Shared DSQs per LLC, one DSQ per LLC. And the machines that we evaluate all of this on are like multi CCX AMD CPUs, and each CCX has one shared L3. For this particular workload, there are three things to keep in mind as we walk through different examples. Is that there are CPU-intensive threads, which are called HHVM workers, because web is HHVM, it's a hip-hop virtual machine. There are a set of IO threads, which do ePOL related work, cache reads, RPC, serialization and deserialization. And then FB tags is what we term the management jobs on the machine that are partitioned away. So this is the high level picture of what we've been working on. Some of this is still work in progress, but it works end to end, and we are able to evaluate various benefits. So the first step that I'll talk about is like what we do when we profile the workload. So the goal is that we have a black box application on the machine, and then using the profiling, we figure out the thread groups of threads that share data, and then push that profile into layer, and then eventually arrive at this sort of configuration for the machine. So the main idea is pretty simple, at least for now. We have clusters where we run like this workload with shadow traffic, and we use perf to basically get samples of memory accesses. Right now, we do not consider latency, cache level for the memory access sample and invalidation events when making various like decisions in the algorithm. And all of this like operates on physical addresses, which like sort of solves the problem where you have two processes sharing data over shared memory. The idea is that we process all of these samples to decide which thread groups are dominant, and then decide the clustering decisions for those thread groups. One of the problems with profiling this stuff offline and then feeding it back into the scheduler is that we need classifiers to decide which threads belong to the clusters that we saw in the profile. So we need some identity for the thread to be able to relate it back to the workloads profile. So one example of this is thread names, which are like obvious. The other thing that we have been like trying out is like application provided metadata. So this is not a priority hint. This is basically just more information about what the thread is doing at a specific time. And then the clustering algorithm is able to use that as a feature or a classifier to split the groups. Like the important point is that PIDs and TIDs are not normalizable because these keep changing across workload runs. So either we profile online, but if we don't, then we cannot use the PID and the TID. So what happens when we actually get the profile? So right now we do a very coarse clustering. We use a very coarse clustering criterion. So we just find the set intersection between the memory access samples that we see for various threads. Now, like the samples themselves are at exact byte addresses. So to basically get useful intersection, we coarsen each sample to the cache line and page granularity to increase the likelihood of finding like overlapping thread groups. So this appears to work well in this particular workload and a few other workloads that we tested for broad classification of threads that share data. So it can identify, for instance, clusters where specific threads run specific request phases. And these, when we compare it to the annotations from the workload itself, appear to correlate well. The other thing is that it is able to identify what we observed by manually profiling the workload, that CPU intensive threads mostly just bounce wake-ups to the IO threads, and they don't appear to share a lot of data. So it makes sense to keep them separate with their own like separate caches. In the future, if we have more diversity in how these workloads access their data, we may need adjustments to the clustering algorithm. Two of the things that we don't admit in the algorithm right now is the code locality, which is mostly because of lack of engineering effort. But temporal aspects are harder, and this is something like I want an opinion of the group as well, and I'll discuss it at the end. So this is what a typical like profile visualization looks like. It's not very useful to basically figure out which threads are overlapping their pages, but you can see that for some of these threads, the physical addresses that I access keeps changing over time. So each slice here is like a 1 second window where all of the accesses in that window are bucketed from 0 to 300 gigabytes of physical address space. So even though these threads, which are the CPU heavy hitters, appear to be intersecting, when you zoom in to these data points, you will see that most of these samples do not actually intersect together. So what are the logistics around doing this sort of profiling? So there's a very strong analogy you can draw to compilers that do feedback-driven optimization and PGO. So one of the ideas that we haven't done yet is to sample these memory accesses continuously in production at regular intervals. This is because we want diversity of the samples, and we want to aggregate information across different profiling runs into the information that we feed into the scheduler. Also, the behavior of the workload, the sort of work it does, keeps changing over a day, over a week, over a month. So we want all of these statistics to be captured by the profiling. And there are similar challenges as PGO in compilers have regarding the freshness of a profile, right? Because suppose that a workload changes materially such that the profile and the result that is produced from the profile is incorrect. So we need some association between the profile and the workload's version to be able to sort of track that sort of disparity between the profile and the workload. Compilers do a lot of heuristics to mitigate the lack of freshness. At least to me, it doesn't appear feasible in this case that we can do something to mitigate staleness. And all of this is done primarily offline right now, mostly to avoid overhead while the scheduler is running. And there is not a lot of precision that we need such that we need to do it online. But this may change in the future if we need to do it. It is possible, but we don't do it right now. All right, so these are the first two steps. And after this point, the scheduling dynamics kick in managing how these thread groups are provisioned, like CPU capacity. So we do soft partitioning of the machine based on the clustered clusters that we receive from the profiling data. So in a simplified way, what we do is give each group a set of CPUs dependent based on its load, and then also allocate these CPUs in a topology-aware manner. So in this particular case, there we have 3 groups, and we greedily allocate the biggest group all of the LLCs that it needs, and then move on to the next group and so on. And when we do not have exact partitioning, we split the remainder of the CPUs proportionally. And this identification of threads to basically fill up these partitions happens using the features that we extracted from the profile. So again, these are like thread names, which can be normalized across machines, or application provided hints like request types along with the thread name. And I want to stress the fact that unless the application provides features as hints, it is difficult to do finer grained clustering. Because even if you can see clusters in the data that you analyze, you cannot set any features for those clusters such that the scheduler at runtime can match them back to the clusters that you saw in the profile. So this information needs to come from the application authors. But our assumption is that this is easier to hint than figuring out what scheduling heuristic makes sense for the application. So there is one particular aspect that I want to discuss because at saturation, like the sizing of the partitions, we care about bandwidth, we do it based on load. But at lower utilization, which is the common case in production, we don't run machines that are completely saturated. We have a lot of variance in the utilization that we see. And this variance we do not see if we capture utilization at coarse time-weighted granularity. Let's say if we are tracking utilization at 1 second or 1 minute, like that's the worst metric to pick. And the variance, if you track the samples at 1 millisecond, can be up to twice or thrice the mean demand that the application places. So, yeah.
Sorry to interrupt. Is this utilization scale or is it a percentage scale?
It is a percentage scale.
Okay.
Yeah.
So this is utilization, but in percentage.
Yes. Yes.
Okay.
So before we observed this behavior, we were doing CPU utilization calculations every 100 milliseconds, every 500 milliseconds. The problem that we hit was that at low load, we were undersizing these groups. And the behavior when you cannot find idle CPUs within your partition is to basically try to be work conserving and find some idle CPU outside your partition. But then you lose affinity effects. So even though we had enough CPUs on the machine, we were not honoring affinity constraints as well as we could. So this is an example, like symbolic example to show what happens here. In this particular case, even though there is no CPU contention in the case before, we end up not spreading to the third LLC, and this leads to a throughput loss at that load level. And since in this case we have enough idle CPUs, it makes more sense for these CPU intensive threads to spread and reduce contention among themselves for the data that they obviously do not share. Now this, yeah.
Can you explain that again?
This one?
Yeah.
So in this particular case, we have enough CPUs to fulfill the application's demand, right? Even the tail scenario, but we were relying on coarse utilization signals, which basically is much less than the P99 utilization that you would see, or the tail statistic that you would see. So we would end up like undersizing the group, even though the optimal decision should have been to spread it across LLC. So that in this case, if the demand spikes, if there is a demand spike, it ends up finding idle CPUs elsewhere. So there's no locality that is preserved for the tail scenario. Anything that exceeds the mean, basically.
So when you say sizing partitions,
Yes.
is it the memory partitions from like MPEG? Or
No,
Intel?
it's just allocating CPUs to different groups. What is the idle CPU selection mask for the group?
Okay, when you say the L3 cache, is it shared between the LLC 0, 1, 2, 3?
No, each LLC is its own L3
Own
cache.
L3.
So this particular bit gets into more vertical integration since we have the data. So one of the things that we saw, and which other people like who operate that service also had an intuition of, is that there is some locality within each request phase. So for instance, if I'm doing something latency critical, in the case of web specifically, the first few 100 milliseconds of that has some locality in data encode. It does something specific again and again across different requests. And in this particular case for web, this first portion is most consequential in terms of their metrics, because this first portion decides how soon the page that you open on your mobile or the web website will show up. So in this case, one of the things that we did to sort of increase the instruction supply to this particular first portion is to give it its own soft partition. And again, the way we did it was, since the application tells us that these particular threads are in the first portion, at every wake up, we can make a decision to either steer the task to the HHVM workers soft partition or the special dedicated soft partition. And it doesn't matter like how many threads are doing the first portion, both partitions will scale based upon their utilization. So the sort of CPU allocation and LLC allocation like scales based on the load. The flip side of this is that once we reach a certain load level, this sort of optimization becomes, for all practical purposes, useless. Because if, for instance, you cannot view the page in, I don't know, like 2 seconds, the client basically just gives up, and the server is, whatever the server returns from the first portion is not useful anymore, even though the rest of the request is still useful. So in this particular case, once we reach a certain point of saturation, we do not really want to make such differentiation at all. So this is yet another signal that we take from the host. The earlier experiments were using CPU utilization of the host as a saturation signal. The more precise signal that we need here is how much idle headroom does this first portion have? And once that idle headroom is gone, we see that basically this is application dependent, but the request latency starts spiking up. So we don't want to keep the differentiation at that point. We want to merge both soft partitions together. So this graph basically shows an example of this sort of load dependent behavior. So the first few minutes of this load test were running the latency based optimization. The green line is the control experiment and the blue line is the test. So the test latency trails the green line. And then once load spikes beyond a certain threshold, both of them end up being mostly similar. And once the load is ramped down, then we get the latency differentiation again.
Sorry, that's with the dynamic remerging of the
Yes.
separated phases? Okay. And without that remerging, the blue line would be even worse latency during the high utilization phase?
Yes. Blue line would be still, blue line would still be lower than the green line, but you would have a throughput hit because the supply to the other phases is being reduced as a consequence of, and that is not something you want. You just want to do as much work as possible once you don't need the SLO. Okay, so like how does this look in terms of numbers? So the improvement in throughput, like once we do all of this together, is around 3 to 4%. So just to contextualize the 3 to 4%, 1% in case of this service is considered significant. It is it is considered a significant improvement. So this 3 to 4% is an outlier, which is sort of motivating. In the sense that we should probably try to apply this to other workloads as well and see the difference. And in terms of average latency, the difference can be anywhere from 5% to 8%, again, dependent on the traffic mix. And since the faster the website shows up for the user, the more likely they are to interact with it and keep browsing it. Like it has a correlation with the revenue that the company earns. And in terms of microarchitectural metrics to sort of like reinforce that this is really working, overall on the system, there is a 6 to 7% reduction in L3 misses and a 2 to 3% improvement in like instructions per cycle. Okay, and any questions until now? Okay, so these, so the next few things are a bit exploratory. I don't have all the answers there. Maybe they, like some of them are even doing approaching the problem the wrong way. So this is mostly food for thought and things that we think are interesting directions to explore in the future. So one of the things that we want to do is basically making this decision of when we are approaching saturation, how do we maximize bandwidth in that case? Because at that point, latency stops mattering as much as it does at lower load. So we can trade it off, but we need a bound on how much latency we will trade. And we also want confidence that when we do something like this, we will actually have a CPU going idle in our previous domain based on our worst case bound. So at low load, this doesn't really help. We tried several experiments where we try to prioritize cache locality by trading work conservation. So it never works. Like this is basically like a lot of people have tried this and it never really works well. The service always experiences a regression. So the rule of thumb in case of lower load is to basically pick an idle CPU wherever on the system. Like cache locality is not important there. But like once we start reaching saturation, it does start making sense to consider how long should we wait for an idle CPU to open up in a previous cache domain. So in that case, we haven't implemented something in the scheduler yet, but something that we did using the profiling stuff was to estimate the distribution of how soon an idle CPU opens up in each LLC. From there, you can establish some sort of probability to threshold curve. Like it is likely to open up in 5 milliseconds, 90% of the time, and 10% of the time you will miss the deadline. So if you have some confidence measure like this, you can first of all ignore this optimization when it doesn't apply, so you don't suffer. And the second thing is you can maximize your chances of hitting the cache when it does apply. So if you have a 90% guarantee, then 10% of the times you waste, you will end up wasting time waiting for a CPU in your previous cache domain. So a very simple approximation of this idea yielded about 1%, 0.6% to 1% at 4 to 5% latency, which is fine as a cost to pay when we are saturated. But this is still an open problem. This is not solved. One of the other things that we want to address is that if we think about cache locality in the context of schedulers, the thing that we care about fundamentally is how likely am I to access the data that I have in my cache over time, right? So that component is currently completely missing from whatever we did. For instance, like the worst case is if we constantly keep rotating data in the cache, there is no benefit in placing you on some shared cache domain. But a lot of realistic workloads do have temporal locality. It's just that it's not a fixed quantity. It can vary depending on the application, depending on the input, depending on a bunch of runtime factors. So a lot of ink has been spilled in academia on using the miss rate of a task, the LLC miss rate, the L2 miss rate. It depends on which domain you are optimizing it for. To figure out
Is hit rate not more important for this particular? Because that shows that you actually reuse data.
You mean the L3 hit rate?
Yeah. So I mean, if you always use new data,
yeah,
then your entire cache content is useless because you've already consumed it. And so what you want to know is if you ever reuse something you've already put in your cache, which is the hit rate, not necessarily the miss rate.
Yeah, I'll try to give it some thought. Right now, I don't have an answer whether it will be better or worse or the same, or maybe the inverse of this. Right now, I don't have.
Maybe they are trying to capture the corner case when some other process is trashing your L3 cache. So that's why they observe the misses more. And if that happens, then they trigger this new domain.
Well, sure, but if you want to know about temporal locality, you should first run the task in isolate.
Yes.
To see whether or not it ever reuses data to a significant extent.
Yeah.
And reuse of data is captured with hit metrics.
So like running it alone in isolation makes sense. But one of the problems with that is, like, do we do that offline or do we do that at runtime? The preference is to do this at runtime because there are a lot of variables that affect these quantities. For instance, the work done by the task itself affects its hit rate and miss rate. So in some phases of the task, it can enter this pathological situation where it's just crashing the cache and then comes back and does something more akin to the normal signal that we get. So it's not clear how to sort of like remove this circular dependency between the scheduler doing something to observe the task in isolation and the scheduler's decisions affecting the metric that it is trying to observe.
Yeah, so I would do offline analysis first, if there is any pattern at all of reuse in a particular phase. Because if there isn't any, you don't need to look for it.
Yeah. Also, like one of the things I didn't add here was observe it while we see the memory access samples and try to capture some pattern from that. But like I haven't done enough investigation on whether it would be high fidelity, let's say, whether it would have like yeah.
So in order to capture the temporal locality, anyway, we need some kind of runtime profiling component.
Yes.
That's some important.
We probably need some runtime signal, yes.
We just use like page faulting to figure out like where.
Yeah, the you mean like as a way to get like collect samples at runtime? Yeah, I think like the problem was that it turns out to be quite heavy-handed. Yeah, that I think like one of the first instincts we had was to do page faults, but it turned out to be pretty expensive.
Wait, expensive in what way?
For the workload.
And page faults are tremendously expensive.
Yeah, but I'm saying, so you just look at like the page faults. Well, I see what you're saying, just having to trigger.
Yeah, because you slow down even if you do it offline, you slow down the workload.
Right.
And if the workload is slow, suddenly the load balancer sends it less work, and there's like some circular. Oh, okay. So this is the final thing. This is even more out there than the previous slide, but like it's an interesting thing to think about, because like what if you could have some abstraction, right, or some sense in the scheduler of how do the interaction of different locality groups when they run on the other side's domain affect, or how sensitive the other side is to some other task coming on to its domain, L1, L2, L3, it doesn't matter, and and basically thrashing its cache. So again, like here, I don't have solutions, but maybe just things that are interesting to think about. One of the empirical like observations we have is that, at least for data center, I'm sure it's true for like other companies as well, but like since the code size is too big, the L1 appears to get wiped out pretty quickly, maybe like in 1 or 2 scheduling slices. So anything you do to try to optimize for that, from the scheduler at least, like we haven't been like much successful. And exploiting L2, we had some experiments where it helped, but nothing that we can like generalize across other workloads. It's either neutral or like doesn't help. So like from the data that we saw, it seems for L3 there are a lot of assumptions we can make, and the time it takes for the scheduler to make a decision is not more than like the locality that domain has. So it takes time for the L3 to get wiped out. So it likely is useful for the scheduler to have an idea of whether which L3 should I choose if, say, all of these threads are sharing data and this one was contaminated by tasks from the other side. Like what's the amount of degradation that this task will have once it runs there? So again, like this is like an open problem.
Just quick question: where is L3 in your memory hierarchy? Is it the first level of shared cache, or is it the SLC?
It's the first level of shared cache. Yeah, on these machines at least. Yeah. Every core has its own L1, L2, but yeah.
Yeah, so it makes sense that private caches are not really relevant to placement.
Yeah, that is it. Yeah.
So in your offline analysis, when you do these isolation, do they meaningfully translate to live production? Meaning,
Sorry, come again?
So if you were to do some ways to say measure the cache hit rate in isolation, so to speak, would that meaningfully translate to the real life workload? Because then your state of your workload is so different that it changes.
Yeah, I like it's hard to have like the right answer is maybe I don't know. Yeah, maybe it does, like maybe it doesn't. There is like definitely temporal patterns that you can see when you visualize things. Like you can definitely see that certain parts of the address space are accessed in a certain segment and certain parts are not. So there are patterns there to extract, but I'm not sure whether it can be something useful at runtime. Or even the footprint. The other problem with this is that these are samples. So these are not the complete accesses, right? So they're already like a small percentage of the total accesses. So
but if you run them long enough over
yes,
iterations, it should cover.
It should give a good approximation. Yes. So these like we did for 1 minute, because it turns out that running the perf mem recording for a minute isn't that doesn't carry as much overhead as we thought. Like compared to something like, I don't know, perfscat trace, right? Which basically produces so much data that like you don't want to run it for maybe more than a second and just get a small slice of the system to inspect. So yeah.
So if you measure the average L3 miss rate of a task, normalize it to runtime, then you can compute from that how many cache lines it will replace for a given amount of runtime.
Yes.
And then compare this to the size of your L3 and then compute pollution metrics from that.
Yeah.
But
you would have to do this computation per slice and then aggregate it, right? Yeah.
Yeah. I don't know if it's useful in the end. It's
Well, so why Peter, why computing L3 miss is not L2 when you are going out of your core cache, and then you would like to probably mark a task as a L3 heavy task and then avoid the situation when you share the L3 with some other L3 heavy task?
Most of this has been focused on L3, right?
Yes, until now.
Yeah, and then you avoid the situation.
But L2 is very small.
But I think what he means is that if you have misses in L2, it means you are creating demand for the L3, right? Yeah.
And then you might compete with some other task greedy on L3, and then you will separate them. Hopefully.
I think the system L3 have much more size than L2 and take more effect on the final result.
Well, yes, but so the L3 cache, it has a huge set associativity, right? So 16 ways, or I don't know how many on this. So you should be fine even for the collision, but it's still, if you use the big data set in L3 and the other task also uses the big set of data set there, then the likelihood that you collide is even for the set associativity is very high. So I would measure the L2 axis.
But it depends on if L2 is inclusive or exclusive in L3. Because some cache hierarchies have every line that is in L2 is also in L3.
I don't know that machine.
Currently, usually is exclusive for ARM.
Okay, but this is AMD. What do you guys have?
Inclusive.
AMD inclusive. Yeah. So have you tried with memory partition instead of the CPU partition?
Yeah, I haven't tried, but my understanding is that you don't want that because the demand keeps varying and you don't want strict partitioning to basically block the case where you exceed that demand. And if there are free resources on the system, you want to use them. So you don't want to hard partition these. Also, the hard partitioning like converges slowly. So here, like we can change the partitions quickly. But like if you want to set like, I don't know, cat, right? Something like cat, then it takes, I don't know, 100 milliseconds to do it. Something like that. It's like a very long time.
I was curious about, you referred to this work in academia that use cap statistics to estimate program phase transitions. I might be out of date, but the work I'm more familiar with on reuse distance analysis, like from Chen Deng and others, almost always is based on a more expensive analysis of the raw reuse distance information that you would get from like binary instrumentation or something like that, where whatever your cache hierarchy, your miss rates are only giving you this very indirect hints about the actual reuse distance.
Yeah, so I think like it's the difference between doing it at runtime versus.
Right, I guess the question I was building up to was, since you're already doing offline optimization and you were showing this sampling of memory, memory footprint, you could also do sampling of Intel PT traces, for example, of the instruction stream, and then do more detailed offline analysis of the full reuse distance if you have the load and store addresses. So I'm kind of curious that there's room there to more explicitly do offline clustering with more information of these program phases.
Yeah, like I'll have to explore. Yeah.
Cool.
was wondering if you or anybody else has ever experimented with the opposite of this, which is like we want to try to perturb as much as possible the migrations of threads, see how sensitive the final metrics at the high level are to the basic temporal locality, right? Because then you can characterize different workloads. This is one specific workload. Other workloads may be less sensitive, but
yes,
a way to characterize that.
Yeah.
So one way could be like you increase the temperature of the schedule, for example, and make it more and more chaotic, and see how much that affects the performance.
Yeah, you mean like looking at the difference in IPC?
Yeah, you can look at latency. You can look at
I think
metrics. But the point is that you don't have to do any kind of instrumentation. You just like make a chaotic scheduler and then see how bad it behaves.
Yeah, I think like this whole space of solution space of perturbing the workload and figuring out some data from there, I think is pretty underexplored. Yes, so I think this would probably make sense. It's similar to what Peter was saying about, like, let's say, like running the workload in isolation, then running it with interference and seeing what happens. Yeah.
I guess I was curious about one other aspect, which is this problem of naming threads persistently between different executions is really painful, and is one that I've fought with a lot in other contexts, like with debuggers or with record and replay debuggers in particular. You have particular identities in a given execution, you're at a given instruction, you have a given PID, but then thread name is a pretty poor approximation for some persistent identity. And you mentioned, of course, the application provided indicators of sort of threat identity. With things like logging crashes, we always use hashes of stack traces. Say like, oh, this crash versus that crash, on different mobile devices, on different servers. Would it make sense to just use some of the stack trace information to?
Your question is, how do we reduce dependence on the thread naming?
Yeah.
So, like, to me, it feels like maybe the stack trace might be more fragile, like, because maybe it changes more quickly than the thread names. Like, maybe that's my, like, I don't know, intuition. Yeah. And the other thing is, like, it's a bit about like the verse being better. Like you like, it's hard to scale this idea of like the application telling the scheduler everything, right? So like we probably use what we have and then vertically add more information. Maybe the stack traces make sense. Like maybe it makes sense to identify like code locality as well, right? You can capture samples of stack traces for threads and find like what function call, but it's expensive, right? You need to symbolize, you need the symbols to be able to figure out. You can't do it from the instruction pointers, right? You need the symbolization. So it cannot, I don't like, it feels difficult to do it online. So it probably can be done maybe during the offline phase.
If you do the offline analysis, you find, for example, very distinct phases in the program, you might then go back to the author and say, well, can you change it to either indicate or switch thread pool at this point? Like, so you always do the various phases in distinct thread pools, just hand over the work to the next thread pool.
And have some way of identifying that. Yeah, makes sense.
It doesn't need to be the same thread again and again. I mean, it has advantages, but also disadvantages. I don't know.
Any question? Yep. Thank you.
Thanks.